We're going to start right off with the very first section of the book. It is 1.1, and in here we'll be talking about definitions and terminology that we'll need for this course. One thing to keep in mind all through chapter 1 is that we are not solving any differential equations yet. We're merely learning definitions and terminology, and then maybe some ways to approximate a solution, and that's it. So the first thing I want to talk about is that we use a lot of acronyms in this class, and I'm a big fan of defining my acronyms first so that I don't leave anybody behind. So one of the big ones is the WRT. I will use that sometimes if the words with respect to are used a lot. If they're only used once, I might just write it out, but that's something you can use as well. Our class is differential equations, so the word differential equations will come up over and over and over again. And so we can simply write differential equation as DE. We will work specifically with ordinary differential equations. And so in that case, we would use the acronym ODE. We will also work with initial value problems, and those are just differential equations where we know a given value at one of our independent variables. And so we call those IVPs. Another one that we won't use in this class because we will use this in this class. Sometimes we'll know information about the boundaries of a domain for a particular solution of a differential equation. And so we'll call those boundary value problems, or BVP. The last one that I like to use a lot because the word therefore comes up quite often, especially when we're done with all of the work that we've had to do for a problem. At the end, we might state something like, therefore, the solution is, and we write that down. And the words therefore, or the word therefore, can be replaced with this little triangle of dots. That is just shorthand notation. And that's seen all throughout mathematics and is a very nice little shorthand to use for yourself. Okay, now let's get started. A differential equation is just an equation. An equation means that there is an equal sign. And in the equation, we're going to see derivatives of one or more of the dependent variables with respect to one or more of the independent variables. Now, we've been kind of trained to think of y as a dependent variable. So this definition would tell me that the dependent variables we would see would be like y, y prime, y double prime, and so on. Okay. And then we've also been trained to think that x is always associated with the independent variable. And so just so that we're back in familiar land and giving them those names, y prime and y double prime for our dependent variables, and they are depending on the independent variable x. Now in real practice, oftentimes the variables are different. They're not y and x, they're anything. It doesn't really matter. And so we'll have to be able to know the difference within our equation. And we'll talk about that as we go through. The next thing is about type and order. In this class, we're going to be working with ordinary differential equations. And an ordinary differential equation is a type of differential equation that may have more than one dependent variable, but it will only ever have one independent variable. Okay, so and here's where I get to the explanation of how I know, based on the equation, what the independent variable is and what the dependent variable is. So this notation dy dx, that's our Leibniz notation for a derivative. The variable on top, so the top variable, that's always going to be the dependent variable. And the bottom variable, that's always going to be the independent variable. So it shouldn't matter whether this is a first derivative or a second derivative or anything like that. the fact that we can see a derivative in Leibniz form, we can already know that in this first example with 3 dy dx plus 7y equals x cosine of x, that the dependent variable is y and the independent variable is x. And in that particular equation, I'm seeing dy dx and I'm seeing y. Those are both functions of the dependent variable. And then I'm seeing the independent variable x, and there's just one of them. Okay, so that's following that ordinary differential equation type. Okay, and this one we don't have more than one dependent variable, we just have the one. The second equation is very similar. It has a second derivative, the d squared y dx squared, but it also has a first derivative. And so both of those are showing me that the top variable is y, so that's our dependent variable. And the bottom variable is x, so that's our independent variable. And again, I also see y hanging out in there, and I see an e to the 3x. So as far as I can tell in that second equation, we have one dependent variable, one independent variable. The last equation is different. The last equation with a dy du and a dx du, I'm seeing two dependent variables. So I see a y and an x. These are both dependent variables. And in the denominators of the Leibniz notation, I just see one variable. And so there's just one independent variable. And because there is just one independent variable, this still satisfies the definition of an ordinary differential equation. Okay? Another type of differential equation is a partial differential equation. So this is going to help us understand the difference between an ODE and a PDE. A PDE has one or more dependent variables. That's still the same as an ODE. But it also has more than one independent variable. That's the difference. And so I have two examples here. In the first example, we've got some funny looking notation in here, and anybody who's taking Calc 3 will know this notation. We don't need to know Calc 3 to learn it though. So the way I say these derivatives is the second partial derivative of t with respect to y both times, minus the second partial derivative of t with respect to x 2 times, is equal to the partial derivative of t with respect to x. Sorry. And so I'm seeing on top that there is just one dependent variable. And so that's great. That falls into the definition for both an ODE and a PDE. But in the denominator, I'm seeing a y and an x. So what I'm seeing is two independent variables. Okay, and because there are two independent variables, I know that this is a partial differential equation. The other thing that kind of lets me know is this funny notation. Instead of d's for the derivatives, we have what are called del's. They indicate that partial part of the derivative. And these are for when we have functions that are functions of more than one variable. The next one, we have del u, del x, we could say that as the partial derivative of u with respect to x, is equal to 7u minus the partial derivative of v with respect to y. So I'm seeing two things on top. I see a u and a v. And so that tells me that I have two dependent variables. And in the bottom, I'm seeing del x and a del y. And so again, I'm seeing two independent variables. I'll slow down with my handwriting for the rest of this video to make it more readable. Okay, so again, partial differential equation just means that there is always going to be more than one independent variable. There could be one or more than one dependent variable. Okay, So make sure to know the difference, because we want to make sure to only work with ordinary differential equations in this class. And the techniques that we learn in this class are not necessarily transferable to a partial differential equation. Okay. So this next paragraph right here is just explaining exactly what I talked about with how do we know which variable is the dependent one, which one is the independent one. So we'll move on to the order. Now, the order of a differential equation is the highest order derivative. This is really similar to when we work with polynomials and we're asked, what's the degree of the polynomial? And we quickly look to see what is the term that has the highest degree, and then we name our polynomial based on that highest degree. And so the order corresponds with the highest order derivative, while a degree would correspond with the highest degree term. But remember, order and degrees are not the same thing. So if we see something like d squared y dx squared, that is the second derivative of y with respect to x both times. But if we see something like dy dx and then all squared on the outside, that is not a second derivative. That is not a second order derivative. That is a first order derivative that is getting squared. Okay, so know the difference between those two things. We have a couple of forms. The most common ones that come up are the normal form and the differential form. So this first differential equation I've given, this is dy dx plus 7x is equal to 3. This is a first order ODE because the highest order derivative is the first derivative, and it is in normal form. All that normal form means is that the dy dx in the equation, the differentials of it are not separated. And to understand what it means for those differentials to be separated, let's look at the next paragraph. So if we were to take that original problem, the dy dx plus 7x equals 3, so I'm actually just going to show it, dy dx plus 7x is equal to 3, and then we multiply everything by a dx, then what happens is this becomes dy plus 7x dx is equal to 3 dx, which is what I have up above here. And this form where we have broken the derivative into its different parts, the differentials, this is called differential form. We'll see both types as we work through this course. And depending on the method that we're learning, one type will be used over the other. And we'll see as we go through. Okay, so let's look at some problems. We need to be able to identify order and type. Hopefully these won't be the most difficult problems. Hopefully they'll be fairly straightforward based on the definitions we just went over. So in question 1, we want to know what is the order and type of each differential equation. We have y double prime plus 2y prime plus y is equal to sine of x. The y double prime is telling me that y is having its derivative taken. So y is the dependent variable, whereas x is the independent variable. Okay, remember we would write y prime as dy dx, and then we would clearly see that the top part of the fraction has a y, so that's the dependent variable. Okay, aside from that though, the order. Well, in looking at this, I see y double prime is the highest order derivative, and so this is a second order ODE. And it's an ODE because I don't have any partial derivatives in there, but more importantly, I have one independent variable, right? That y double prime and that y prime and that y, they're being added together and giving me back a sine of x. That means that each one of them must just be some function of one variable x, okay? So second order is the order, and then ODE is the type. All right, the second one, I have y double prime plus 2 in parentheses y triple prime all squared plus y double prime is equal to 0. Now, this one's trying to be a little bit tricky with that square in there, but overall I can still recognize I have a y prime, a y double prime, a y triple prime, and y triple prime is the highest order derivative. The fact that it's squared does not make it a 6 prime, okay? That just means take y triple prime and multiply it by itself. That's it. Now, this particular one is, this one is going to be third order. And then the type, well, again, I don't have any like explicit independent variables sitting there, but I have to assume that y prime, y double prime, y triple prime, those are normal derivatives like we would see in a Calc 1 class or a Calc 2 class, like dy dx and d squared y dx squared, and so on. And so if there's that y prime and I can associate that with dy dx, that means I'm not associating it with del y, del x. And so I can assume that this is an ODE for the type. Okay, on the flip side, in number 3, we've done things differently. Here I see that partial notation. I have that del thing showing up. And so in there, I'm looking at the order of my partial derivatives first. I see a del squared u and a del squared u. So right away, I can see I only have one dependent variable, but it's the second order. And so this is a second order problem. But the type, let's look at the denominators. I see x squared and I see y squared. There are two independent variables, and so this has to be a partial differential equation. That is the type. Okay? All right. Now, we want to see an example of the normal form of a linear nth order ordinary differential equation. So that's putting together like a whole bunch of stuff. In particular, like this is something you would see in the book. We will most likely stick with differential equations that are maybe at highest fifth order, okay? Most of them will be second or third order at most, but we'll see a few that are higher order. And so when we want the normal form of a linear nth order ODE, we want the nth order derivative to show up. And the normal form means that we want it to not be split apart. We want the Leibniz notation. We want that fraction in there. We also need that all of the coefficients, so our coefficients in this case are called a sub n of x, a sub n minus 1 of x, all the way down to a sub 1 of x, down to a naught of x. Those are all the coefficients of the dependent variable and its derivatives. So we'll name them that. These are the coefficients of the dependent variable and its derivative, or derivatives. And they are, if you notice, when we use that notation, a sub n of x, these are all functions of x, the independent variable. And so I can put that down here in my little box where I've got function of an independent variable. I didn't type in the x because, as I said before, it's not always x, right? And so we don't want to get hooked on x and y in our problems because then it's hard to translate our definitions when the letters change. But in this particular case, we have x's and y's. Now, on the right-hand side of the equal sign, we have a function of the independent variable hanging out all alone, all by itself. It's like a constant, but it's not a constant. Well, it could be a constant. It could be 7. It could be 0. It could be 3x. But what it is not is it is not a function of y. There are no y's multiplied with it. Y does not exist with it. It is simply a function of x, and it could be a constant, okay? And so this is our normal form of a linear nth order ODE. The reason that it's called linear, we're going to get to that right below, okay? So this classification by linearity, we need to know the difference between linear and nonlinear. An nth order differential equation is linear if the following things hold true. The dependent variable, and I'm going to use y just so we have a letter in our head, the dependent variable y and all of its derivatives, so that would be the y prime, the y double prime, and etc. They must be only of first degree. So we won't see some derivative hanging out and then getting squared, okay? The other thing that has to be true is that the coefficients of the dependent variable and all its derivatives, they have to depend only on the independent variable. So if there is like a y in the coefficient for the second derivative, that's a big problem. It is not a linear equation, okay? So an nth order differential equation is nonlinear if either of the following holds true. The dependent variable or any of its derivatives are second degree or higher. So we want first degree y's, y primes, y double primes, and so on and so forth. The other thing, if the second thing is broken, then it's nonlinear as well. If any of the coefficients contain the dependent variable, then we have a nonlinear differential equation. So let's see if we can sort this out here. I have a couple of questions. Are the following differential equations linear or nonlinear, and why? So let's look at the first one. The square root of 1 minus y squared times y double prime plus e to the xy times y prime minus sine of x times y is equal to x squared. I'm going to go through and highlight the terms that are good for being linear. So this minus sine of xy and this x squared, those are good. Those would be linear terms, right? The y isn't being squared. The coefficient with y is a function of the independent variable x. On the right-hand side, we have a function of the independent variable x. And so those are good terms. The problems are right here and right here. So in front of y double prime and in front of y prime, I have functions that have y's in them. Y is the dependent variable. Right up above, it says the dependent, in number 2 for nonlinear, it says any of the coefficients contains the dependent variable, then we know our differential equation is nonlinear. So this right here, the square root of 1 minus y squared, is a coefficient with the dependent variable. And same with e to the xy. So those are both no good, and that is why we would say that this is a non-linear, and it's because of the square root of 1 minus y squared with the y double prime and the e to the xy with the y prime. Okay? The second one, we have 3x y double prime plus sine of x y prime minus x squared y is equal to e to the x cosine of x. So the first thing I want to look at is the degrees of each of my derivatives. So I've got y double prime, it's not getting squared. I have the y prime, it's not getting squared or anything, nothing's happening to it. The y is good. These are all first degree. And that's good. That satisfies the first criteria for being linear. The second criteria has to do with the coefficients in front of each one of them. And so I look closely at those. I've got the 3x, I have sine of x, I have minus x squared. And on the right-hand side of the equal sign, I have e to the x cosine of x. All of those are functions of x. So all coefficients are functions of the independent variable. Independent variable. So the differential equation is linear. And that's it. That's all we have to do. Obviously, I'm spending more time with these than you might have to in any sort of homework, but I just want to make sure to address all the finer points. All right. We're only going to work with linear ordinary differential equations. We do not want to work with nonlinear, and we do not want to work with partial differential equations because this class is the class of like introduction, right? We need to master the art of working with linear ODEs before we step it up a notch and work with nonlinear ODEs or partial differential equations. But we need to be able to identify when we see nonlinear or PDE so that we know, oh, we don't know how to work with those. All right. Some of the notations that are common for derivatives, we have the traditional Leibniz notation, where you see dy dx, d squared y dx squared, and so on. There's a tensors or dot notation, where you see a dot over the y to indicate first derivative, or two dots over the y to indicate the second derivative. As you might be able to imagine, that becomes kind of cumbersome. I mean, if you have a fifth derivative, then you would have a y with 5 dots over the top of it. So we don't use that one. The third one is prime notation, and that's where you see the y prime, the y double prime, y triple prime. If we go beyond a triple prime, we write the number of the order in parentheses so that we don't accidentally mistake it for a degree. So the fourth order derivative would be y raised to, in parentheses, a 4. We use that notation all the time, okay? All right. We have different types of solutions for ordinary differential equations, and the reason for that is that sometimes when we find a solution, the method that we use to solve the differential equation gave us an answer where we could solve for y. But sometimes it gives us an answer where we can't solve for y explicitly, okay? So we have to know the difference between explicit and implicit. Explicit means you can like read it out. Y is a function of x. So like y equals something in terms of x. We might have to go hunting for that. Like we might get an answer like x squared plus yx is equal to c. But we're being asked to give the explicit solution. So the explicit solution means solve for y. It also means that you even can solve for y. So if we solve for y here, we would first subtract the x squared and get yx is equal to c minus x squared. And then we would divide both sides by the x and get y is equal to c minus x squared over x. We may even go further and rewrite it as c over x minus x. And now we have y is a function of x. And so that is an explicit solution. Implicit means we're never going to be able to solve for y. And so the hope is that in WebAssign, they kind of know whether you're able to solve for y or not. And so they don't ask you for an explicit solution unless you can get one, okay? So in this particular problem, when we get an implicit solution, we would just move all the variables to the left of the equal sign and keep a number on the right of the equal sign. So let's look at this example. We have x squared y plus y squared plus e to the xy is equal to c. If I tried to solve for y here, I wouldn't be able to. The first term, I see y by itself. And so I'd be like, oh, just move everything else over and divide by x squared. Well, that doesn't work, because if I move the y squared over, then I have y on the other side. I'm not looking for y in terms of y. An explicit solution is y in terms of x only. We can't do that. If you focus on the second term, you might think, oh, move everything over and take a square root. But then you're going to have y equals and then some stuff where there's x's and y's in it. So again, that's not going to work. And the third term, e to the xy, might make you think, well, we can move everything over and take a natural log of both sides. Nope, still not going to work. You're going to have y's on both sides. It will not be an explicit solution. And so an implicit solution means you, and I'm going to use the words may not be able to solve for y. And I say may not because you may be asked for an implicit solution even when you could get an explicit solution. So it's basically saving you the work, okay? All right, the third type of solution that we get is the zero solution, and that is a solution for many of the ordinary differential equations that we're going to work with, but not all of them. However, it's kind of a boring solution, and therefore we have a name for it. It's called the trivial solution. So the trivial solution is just y equals 0. We typically do not consider it in our solutions when we're solving ODEs unless it is the only solution that there is, okay? When we're solving differential equations, we're going to come up with a family of solutions, and that's, if you think back to Calculus 2 when we were integrating an indefinite integral, we always had that plus c, remember that? And that's coming from, it's a constant of integration. We're going to use methods that may or may not use direct integration. So you may or may not realize you need a plus c. And as we learn each method, I will point out where you put your c, okay? But so when we're solving a differential equation, if we have an equation that just has a dy dx and no other higher orders, then that means that somewhere in the work that was done to find the solution, an antiderivative was found. And so we just have to account for that by putting in the plus c, okay? And we're going to call the plus c a parameter. Okay, and so when we have an equation that has dy dx, the solution that we get is called a one-parameter family of solutions, something like that, okay? An example of something you might see is like y is equal to 1/3 x cubed plus e to the x plus c, something like that. There's only one unknown, that's the c, and so we call it one parameter. But if we work with a differential equation that has a higher order within the equation, like a second order, then we must consider that there could have been two integrations, which would give us two constants of integration, plus c and plus d. We call these parameters again, and for a second order differential equation, we would say that there's a two-parameter family of solutions, okay? We won't always see them as plus c and plus d. We might see them as multipliers on the functions, and that has to do with the methods that we use to solve. So in general, we just need to wrap our heads around this. If we have a first order differential equation, we get a one parameter family of solutions. If we have a second order, for a second order differential equation, there's a two parameter family of solutions. And in general, if we have an nth order ODE, then we will have n parameters, and we would say we have an n parameter family of solutions, okay? So the order of the differential equation gives us information about how many parameters we have. And if we had any points that the solution passed through, we could solve for those parameters. And this is alluding to that idea I spoke of in the very beginning of this section. It's alluding to that initial value that we might be given in a problem. All right, another definition is about the interval of definition. We've worked with domain a lot all through algebra and trigonometry and calculus 1 and calculus 2, and we're still working with domain. Domain never goes away. It's always important. So when we find a solution to an ODE, you may be asked for the interval of definition. And what you need to know is that these two things, interval of definition and domain, they're kind of interchangeable. And I say kind of because there is a slight difference, okay? You can think of them as the exact same thing, but we're going to become a little bit more picky in how we determine our domain for an ODE. So the domain of a function as a solution might be different from that of just a regular old function. A solution's domain is going to be further restricted by any of the work done to find the solution and by the derivative of the solution. So just for an example really quick, if we were to integrate 1 over x, just looking at 1 over x, I know it's not defined at 0. 0 is a bad guy. We would end up dividing by 0, and that's not good. And so even to integrate this, we could only integrate it to the left of 0 or to the right of 0. But the actual antiderivative of 1 over x is the natural log of the absolute value of x. And so in the methods that we use, we often end up dropping that absolute value symbol. And then we have to put in this, x is greater than 0, strictly greater than 0. We cannot have x equal to 0. And the reason that is our domain is because the natural log of x has a domain of x greater than 0. Okay? And so you will need to find only one interval of definition for our solution. You don't need two. And as we move along through here, I will point out where sometimes we have two intervals of definition and how is it that we decide which one to pick. Okay, because sometimes it won't matter, but sometimes it will, and we need to know what those times are. But we're not there yet. Let's look at this example. We want to determine a domain of y equals the square root of x plus 7 if A, y equals the square root of x plus 7 is just a function. And in B, if y equals the square root of x plus 7 is a solution to a differential equation. So let's focus on A first. In A, y equals the square root of x plus 7 only has issues if we try to plug in a number for x, and whatever the result under the square root is ends up being negative. We can get 0 under the square root. It's okay to take square root of 0. So for my domain here, I start off with writing the inequality x plus 7 must be greater than or equal to 0, and I solve that. So x is greater than or equal to negative 7, and then I could write my domain, and it is an interval notation from negative 7 up to infinity, including the negative 7, okay? But if this same function is a solution to a differential equation, that's part B, now we need to know where y and y prime are defined. Because y prime is in the original equation, so if we pick a domain and our original equation isn't defined on that domain, then we've got problems, okay? And this is kind of like the invisible part. We can easily forget that this needs to be done, but it does. Okay, so we already know the domain of y. We need a domain for y prime, which means we need to find y prime. Y prime is going to be the derivative, d dx, of, and I'm going to write the x plus 7 under the square root as x plus 7 to the 1/2, and then I'll take that derivative. It's going to be 1/2 times x plus 7 in parentheses, all raised to the negative 1/2 times the derivative of x plus 7, which is just 1. And this simplifies to be 1 over 2 square root of x plus 7. So what I'm seeing is I still have a square root of x plus 7. It's not very different from the original function, but the issue is now we're dividing by the square root of x plus 7. That means that we can't have a 0 under the square root because the square root is in a denominator. And so we would have to say here for the domain that x plus 7 has to be strictly greater than 0, which means x is strictly greater than negative 7. And so the overall domain here for in interval notation is in parentheses, negative 7 up to infinity. And that's it. So you will be asked some questions where you have to determine the domain of a solution to a differential equation, and this is that extra step you have to take. You've got to look at the derivative and its domain. All right, here's an example. This topic is actually a whole topic, but I teach it by example. You have some problems where you're asked to verify that a function actually is a solution to your differential equation. And this goes back to, well, it kind of goes way back to, elementary algebra when you're first told, hey, solve this equation, and then you get an answer. And then they say, check your answer. And you do that by plugging it in. We're going to do the same thing. So here we're being asked to verify that y equals 5 tangent to 5x is a solution to y prime is equal to 25 plus y squared. We're also being asked to give an interval of definition for the solution. So I'm going to first verify. And so the verify part, what I do is I take y equals 5 tangent of 5x and calculate y prime, which y prime, it looks like we've got 5 secant squared is the derivative of tangent. So secant squared of 5x times the derivative of 5x, which is 5. So we get 25 secant squared of 5x. So we're going to take y and y prime and substitute them into the differential equation. Okay, I have my y, I have my y prime. I'm going to plug them into y prime equals 25 plus y squared. So I get 25, that's a funny 5, secant squared of 5x, that's my y prime, equals 25 plus y squared will be, I'm going to put the 5 tangent of 5x all inside parentheses to square it. Okay, so left-hand side, 25 secant squared of 5x, that's the y prime. And then on the right-hand side, I have my 25 plus my y getting squared. Okay? All right, when I write this out again, what I've got is 25 plus 25 tangent squared of 5x. This is actually a Pythagorean identity. And so, yeah, this is totally true. If we think back to our Pythagorean identities, we know, I'm going to just do the blurb. So we know sine squared of x plus cosine squared of x is equal to 1. And if I want to see what the Pythagorean identity is that includes secants and tangents, then I should divide everything by a cosine squared. So then I get sine squared of x over cosine squared of x plus cosine squared of x over cosine squared of x is equal to 1 over cosine squared of x. And then I simplify that. Sine over cosine is tangent, so that's a tangent squared of x plus a 1, and 1 over cosine squared is secant squared of x. Now, if I was to throw a 25, like multiply everything by a 25 here, I would have 25 tangent squared of x plus 25 is equal to 25 secant squared of x. And then we can see how that is the Pythagorean identity that we're working with in our ODE. Okay, so the equality holds because this is a Pythagorean identity. Okay, and that's it. Like, I've shown it. Some work out really nice like this. Sometimes there's more work involved. And sometimes you have to really think back to things that you've forgotten, like Pythagorean identities, including secant and tangent. Okay, the next thing is to give an interval of definition for the domain. So let's work with that. Interval of definition. So if we want the domain of y equals 5 tangent of 5x, then we need to think of it in terms of sine and cosine maybe. So this would be 5 times sine of 5x over cosine of 5x. And then maybe it's a little bit easier to see that tangent is not defined anywhere that cosine of 5x is equal to 0. So this, so let's see, y is not defined when cosine of 5x is equal to 0. Okay, and now I'm going to be really nitpicky and go back up here and point out that it said give an interval. So it's not asking for all the intervals in the world, it's just asking for one of them. Okay, so cosine is equal to 0 at pi halves, negative pi halves, 3 pi halves, negative 3 pi halves. It's equal to 0 at all of those. Okay, and so this is when 5x is equal to plus or minus pi halves, plus or minus 3 pi halves, and so on. Okay, so all the odd multiples of pi divided by 2. Well, that's 5x. I want the value of x where bad things happen. And so that means, or when x is equal to plus or minus pi over 10, or plus or minus 3 pi over 10. Okay? So we know where y is not defined. And right away I could say like one interval would be from minus pi over 10 to positive pi over 10. Everything would be cool inside of there. But I'm not quite done because I also need to look at the domain of, domain of y prime, which is 25 secant squared of 5x. Remember that secant squared is 1 over cosine squared. So this is just 25 over secant squared of 5x. And there are no changes in the domain. Sorry, I wrote that as secant squared in the denominator. I meant to write cosine squared of 5x. So both tangent and secant squared have the same domain restrictions. So let's just write that. These are the same domain restrictions. So nothing extra gets added. And so an interval of definition is, well, one of them would be from minus pi over 10 to positive pi over 10. Or we could go from pi over 10 to 3 pi over 10, or any other variation, okay? When it comes to listing 1, I typically will choose the one that includes 0 in it, or something close to the axis, or the origin, sorry. And that's it. We're done with that one. So I could enter this for an interval, and the work behind showing that the solution actually was a solution is written up there. Now, this one was pretty straightforward. I want to also talk about what happens if we're asked to verify that an indicated expression is an implicit solution to the DE, and then find at least one explicit solution of the DE. So in this particular problem, you have to remember, we have not learned how to solve differential equations at all. We are being given the solution and we're being asked to check it, okay? So to verify an implicit solution, what I need to do is find how to implicitly differentiate the implicit solution and then put in differential form to see if it matches the differential equation that's given. Okay? So implicitly differentiating, we're having to recall so much already just in day one. That means we're going to take d dx of the entire equation, the minus 2x squared y plus y squared is equal to 1. We're going to take d dx with the understanding that y is a function of x, so the derivative of y with respect to x is y prime, or dy dx. I'm going to write it as dy dx, okay? So when I take d dx of minus 2x squared y, I have to recognize that I have a product there and need a product rule. When I take the derivative of y squared, I have to recognize that I have a chain rule, and I have to apply the chain rule. So let's see how this works. I'm going to go really step by step right here. Okay, so if I take the derivative and send it through, I've got d dx of minus 2x squared y plus d dx of y squared is equal to d dx of 1. I'll focus on the first term. The derivative of, I'm going to treat these like two things here. So I've got a minus 2x squared, and then I have y. That's my product. So the derivative of minus 2x squared is minus 4x times the second thing, which is the y, plus the first, which is the negative 2x squared, times the derivative of y with respect to x, which is dy dx. I'll clean that up in a minute. Plus, now the derivative of y squared, I have to recognize that I have a power rule there. So I'm going to go ahead and take the derivative of the power rule. So it'll be 2y, but the chain rule says, now take the derivative of y. Well, the derivative of y with respect to x is just dy dx. And this is all equal to the derivative of 1 with respect to x, which is 0. Okay, let's keep going. Let me just clean it up. I have minus 4xy minus 2x squared dy dx plus 2y dy dx equals 0. Now remember I said that we need to get this in differential form. That means we need to multiply everything by a dx to get it in that form. When I do that, I get minus 4xy dx minus, when I distribute the dx to the second term, the dx's cancel. I get minus 2x squared dy. That happens again in the third term, so I get plus 2y dy, and that's all equal to 0. Now I'm going to keep my eye on the ball, which is the differential equation up above. It looks like I should maybe factor out a minus 2 or something like that, because I'm seeing I have like double what the original differential equation is, and my minus signs are in the wrong spot. So I'll do that. Minus 2, that leaves behind a 2xy dx plus x squared dy minus y dy is equal to 0. Now, I could divide both sides by that minus 2, and 0 divided by minus 2 is 0. So that minus 2 just has no effect on our differential equation. So I'm going to do that, and at the same time, I'm going to combine like terms with the x squared dy minus y dy. And so I finally have 2xy dx is equal to, plus, in parentheses, x squared minus y dy is equal to 0. Now, is that what my differential equation was? It is. It's exactly it. So this is the differential equation. But I started with the solution. So I took d dx of the implicit solution, supposed solution, and I got back the differential equation. So I'm good. The solution, or I should say the expression is an implicit solution. Now, they want us to do something a little bit more. They want us to come up with an explicit solution. And so that means we're supposed to play with this minus 2x squared y plus y squared equals 1 and solve for y. Okay, so let's see if we can do that. I'll write it again down here. So let's find an explicit solution, because it says find at least one. And so we're working with minus 2x squared y plus y squared equals 1. I'm noticing that this is kind of a quadratic in form sort of problem where I'm dealing with quadratic in form with y. So I'm going to rewrite this so that it looks like it's quadratic in form. So the y squared would be written first. The minus 2x squared y would be written second, and then I'd bring the 1 over and write it as minus 1 is equal to 0. So this is quadratic in form with y. It's actually just quadratic, but what's weird is what a, b, and c are. A is equal to 1, b is equal to minus 2x squared, and c is equal to minus 1. And I'm writing those out because the only way for me to solve for y is to use the quadratic formula. And so the quadratic formula says that y would equal minus b plus or minus the square root of b squared minus 4ac all over 2a. So plugging everything in, minus b would be a positive 2x squared, plus or minus the square root, b squared would be 4x to the fourth, minus 4ac would be minus 4 times 1 times minus 1. That would be plus 4. All divided by 2 times a. A is 1, so let's just divide by 2. I can simplify this a bit. I have 2x squared over 2 plus or minus. Under the square root, there's a 4 common to both terms. And so I can pull out a 4 and take the square root and have 2 square root of x squared plus 1 over 2. And then I can simplify one more time and say y is equal to x squared plus or minus the square root of x squared plus 1. Both of those work as solutions. We could say one explicit solution is y equals x squared plus the square root of x squared plus 1. And the other one has the minus sign. Okay? And that's all I've got for this section, so hopefully that helps you with your work. And please reach out if there are any questions at all.